Welcome back everybody. This is our 10th video or class in JEE Mains previous year question for chapter moving charges and magnetism. Before this video we have made 9 videos in this series and all of those videos are available on our YouTube channel in the playlist section. We have also started similar series for NEET previous years, so you can go to our channel and in the playlist section can find those videos also. And if you find these videos useful, then do press the like button, share them as much as possible, and subscribe to our channel. It will be a lot of help. Also, if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. With your donations, we will be keep on making these videos on regular basis. Till then, again, uh, let's start the video. And I think we have completed around 60, question number 60 or 70. Which one? The last one? Yes, this was the last one. Question number 71 was the last one of the previous video. Now let's start with the next one. And I think it is the same as the previous one. Okay, so this question got repeated on 2 times. So it is the same. And answer was option A, I think. Or let me check. Twice. Okay, twice. So answer was option C. In this case, option C will be the right answer. Moving to the next one. Let's slide it slightly. So here we have a wire carrying current I is bent in the shape A, B, C, D, F, A as shown, where rectangle A, B, C, D, A and A, B, D, E, F, A. So A, B, C, D, A, we have a rectangle in, we can say, XY plane, and we have another rectangle AFEDA in the XZ plane, and they are perpendicular to each other. If the sides of the rectangles are length A and B, then the magnitude and direction of magnetic moment of that loop. So we have to find out total magnetic moment of this loop. And when we have such type of question where our structure or our shape is in multiple dimensions, like here we have one part of this square in, or this rectangle in xy dimension or xy plane, and another in the xz plane. So what we do, we have to divide that rectangle into their respective planes. Means we do calculation for xy plane separately, and we will do calculation for xz plane separately. And for doing that, we have to make them complete loop in their own plane. Like let's talk about the loop, or we can say rectangle A F E D E. Now, if we start from A, then go to F, then go to E, then go to D, then there is no direct path from D to A. So what we have to make here, we have to connect this D to A so that we can have a complete loop here. And that can be done via this method. That what we do here, we connect as direction of current will be from E to F to A. So direction of current should be going A to D. So we connect A and D like this. So we connected A and D like this, and as a whole, before this connection, there was no connection between A and D. So there must be no current flowing between A and D. And as we added a connection, so we added a current going from A to D. So we must, we can say, uh, reverse this value of current, or we must make this current's effective value as zero. As we added current from A to I, then we must add, A to D. We added a path for current from A to D. Then we must add a reverse path from D to A, so that net current in this path is in equal and opposite direction. So net current becomes out to be zero. So we also add a reverse path from D to A, and this reverse path will become part of the second loop. So here we will have something like this. We will have two loops, and let me draw them. So our loops will look like something this, that we have a loop A, B, C, D, and this side AD, this is represented by the red arrow which we drawn here. This is the red connection we just made here between D and A, and that A and D in the second loop. This is the blue connection we just made here. So that's how we are getting here two loops, and direction of the flow of current in both loop. In this loop, it is something like this. Here, here, and on the second loop, direction of current is something like this. So our direction of current also matches with the loop of the current, and in which we added these two connections between A and D and D and A, and these connections must be such that they cancel equally each other, so that as a whole we don't have any current between A and D. So now what we do, now we will find their individual magnetic moments, and then we add them using vectors. So, as per the axis and using the right hand screw rule, here current, as we seen from the upward direction of the screen, the current is moving according to us in an anti-clockwise direction. So, magnetic moment of this loop, this upper loop, will be in the positive x direction, and magnetic moment for the this lower loop A B C D A will be in the upper direction. So let's write down and the value of magnetic moments. So magnetic moment for loop A F E D A, it is I times the area, and we know that area here is for both of the loops at sides are A and B. So area is A into B into current I, and direction for this is in positive X. Similarly, moment for the second A, B, C, D, A is AB times I into positive of J. So total magnetic moment will be AB and I common into I plus J, and we can say magnitude will be, if this is vector form, if we find the magnitude of this vector, that it will become root 2 AB times I. And if we have to find the direction, as this is when we write direction, then we write direction in the form of unit vector, and unit vector of these two will be I plus J by root 2. So okay, here we have the upward direction is considered as Z. Here upward direction is considered as Z and this one as Y. So this is Y direction and this will be in Z direction. So here we will have Fe in J and this will be in K. So J, K, and this will be J and K. So we made that mistake. So answer will be option B, root 2 ABI, and along this direction J plus K by root. Moving to the next one, a small circular loop of conducting wire has a radius A and carries current I. It is placed in a uniform magnetic field B perpendicular to its plane, such that when rotated slightly about its diameter and released, it starts performing simple harmonic motion at time period t. The mass of the loop is, so we have to find the value of mass of the loop. So here basically we have a small circular loop which is placed along its diameter, or we can say which is oscillating across its along its diameter in the form of simple harmonic motion. And we have a field, magnetic field, that is perpendicular to its plane. So suppose this is our loop, and it is oscillating about its diameter. So let's draw it. Let me draw the diagram properly first. Now, suppose this is the red line represents its diameter. Now we know that magnetic moment of this loop, as it has some current I, suppose value of current is I, then magnetic moment will be current times area. So I times, that is current, into area is pi a square, where a is its radius. As I think, yes, radius is a mentioned in the question. Now we know that direction of the magnetic dipole moment, according to, we can say, right hand screw rule, here in this case will be upward. This will be the direction of M, or magnetic dipole moment. Now coming to the second part, that magnetic field is also perpendicular to the plane. So let's take magnetic field in also in the same direction. As mentioned, that magnetic field is also perpendicular to the plane. So we have two variables, two things. This is magnetic dipole moment and this is magnetic field. And in this scenario, if we calculate the torque, as we know that torque is given by M cross B, cross product of M and B, and as both M and B are in same direction, so torque will be zero. Now what happens, that this we can say this coil or this loop is rotated slightly by small angle. So it is rotated slightly. So if we see its diagram from one of the side, we can say diagram looks like something like this. That this is the plane of our, this is our coil, or this is our loop, and here we have its magnetic dipole moment perpendicular to it and magnetic field perpendicular to it. Now we rotate it slightly. So what happens? This was the original direction and we rotated it slightly. So our coil or our loop becomes like this. So its magnetic dipole moment M is also rotated by this angle, and magnetic field stay the same, as magnetic field is not getting rotated. So this is the angle theta here, that is between magnetic moment and uh, magnetic dipole moment and the magnetic field. So now in this scenario, torque acting, or restoring torque, we can say it, restoring torque will be M cross B, and it will be M B sine theta. And as this theta is very small, so we can write it MB into theta, and comparing it to torque is equal to C theta, where C is the restoring constant. We can find out that C, value of restoring constant, is magnetic moment times magnetic field. So it will be IB into pi a square. Now from the SHM, we know that omega is given by K by M for non-rotating body, and C by moment of inertia I for a non-point object. which is rotating. So where c is the uh, restoring constant and I is the moment of inertia. So writing value, omega is 2 pi by t, value of c is I b by a square, and t is the here I is the moment of inertia, and as this is a ring and moment of inertia of a ring about its diameter is half mr square. Half m radius is a, so a square get cancelled, and we are left with 2 pi by t is equal to under root 2 pi I p by mass. And from this we can write out that time period will be, it will be 2 pi times root m by 2 pi ib, and it can be further written as 2 pi m by ib, which is our option C. So that's how you find solution for such type of problems. Moving to the next one. Two wires A and B are carrying currents I1 and I2 as shown in the figure, and their current is in opposite direction. Separation between them is D. A third wire D carrying a current I is also kept parallel to them at a distance x from A such that net force acting on it is zero. So net force on this wire C is zero, then the possible value of x are. So let us first slide down its. Now as we have to place here the third wire, and which that wire should be in a balanced condition as per the value, and current in third wire will be either parallel will be parallel to one of these. It either can be upward, so parallel to A, and it either can be downward, then parallel to B. Now we know that wires with the same value of current or same direction of current attract each other, and wires with opposite direction of current repel each other. So if we place this wire C in the midway between the two, suppose at x distance, and direction of current is upward, then what will happen? These two wires, wire C and A, have a same direction, current in same direction, so they will attract each other, assuming A and B are fixed. So on C, due to A, there will be force towards the negative x direction, and C and B have current in opposite direction, so they will repel. So it will further repel the wire C. So on C, there will be net force on the negative x direction. If we reverse the direction of the current, if we reverse it, if make it downward, now C and B have the same direction of current, so C will be attracted towards B, and A and C have opposite direction of current, so it will be repelled again towards the B. So now again it will have net direction of force, that will be positive x direction. So it means we cannot place wire C between A and B. We have to place it somewhere else, or we can say outside. And as mentioned that the distance of wire C from wire A is x. So let's try to place this wire on the left side of wire A, and let's see what happens. Either can it be balanced or not. So suppose we place wire C here. So this is wire C, and this distance is x now. Now assuming it has the same direction of current as of wire A, then now what will happen? Now wire C and wire A will attract each other, and wire B and wire C have opposite direction of current, so they will repel each other. So now there is a possibility that these forces can get balanced. So we will use this method here, to find out the balancing position or the balancing length. So we know that in case of parallel conductors, force per unit length, force per unit length acting between those is equal to mu node by 4 pi into twice of values of current divided by their distance. So this is the force per unit length. And as we are considering all of these three conductors as infinite length conductors, so we assume that force per unit length acting on conductor C will be equal due to both A and B. So let's suppose current of conductor C is I, then force, attractive force due to conductor A, force per unit length due to A will be mu node 4 pi twice of I1 into I divided by x. Force due to B will be mu node 4 pi twice of I2 into I by x plus d. So now equating both of these, we can easily say that mu node 4 pi get cancelled, 2 get cancelled, and I also get cancelled. So we will left with I1 by x is equal to I2 by x plus t, and from this we have to find the value of x. So it will be x I1 plus dx is equal to x I2. So we can say x into d is equal to x of I2 minus I1, and value of x is xt by I2 minus I1. Okay, no, this can't be done in this way. We made a mistake. So it is xi1 plus I1d. That was the mistake. xi1 plus I1d and I2x here, and we will have here I1d is equal to I2 minus I1 into x, and x1 will be I1d by I2 minus I1. So I1d we have, I think, here the last option which is missing for us, I1d by I2 minus I1. So this will be the option D will be the right answer. And same can be done with the help of wire, taking this wire on the right side. We will get the same answer just with negative sign. So the answer will stay the same. So option D will be the right answer here. Moving to the next one. A rectangular coil, dimensions are given, with 100 turns carrying current clockwise direction kept at the origin in the xy plane. Magnetic field of 1 Tesla applied along x-axis. If coil is tilted about 45 degree about z-axis, then the torque on the coil. So let's first draw the coordinates. So it is kept in xz plane. So let us suppose this is x and this is z, and our rectangular coil is in xz plane. This is our coil. Now magnetic field is applied along x-axis. So magnetic field is applied along this axis P, along the x-axis, and we know that magnetic dipole moment and its current is in clockwise of this coil. So using right hand screw rule, we can find out that uh, magnetic dipole moment of this dipole will go perpendicular to it and in the negative y direction, because here as this is x, this is y, z, so this will be y axis. And if you use right hand screw rule, you will be able to find out direction of the magnetic dipole moment. It will be in the negative z direction. So m will be minus, due to negative z direction, negative y direction, into the area. Area is 5 into 100 into 2.5 divided by 100 into n, because we have 100 tons, and with J sign. And current also needs to be there, so 3. So this will cut, and here we will have approximately 7.5 multiply 5, so 35 plus 2, 37. It will be negative 37.5 by 100 J. This will be the magnetic dipole moment. Value of magnetic field is known to us, that is B, and it is 1 Tesla in x axis, so it is 1 I Tesla. Now coil is tilted about through 45 degree about z axis. So this coil is now tilted about 45 degree around z axis. So if we plot z axis here, it is rotated about z axis. So I can say, if we draw the coil, I only draw the coil, and this is our z axis. So initially coil was something like this. Initially this was the coil, and now coil has rotated about 45 degree around z axis. So now coil looks like this, something like this. Now our coil is like this, and this angle between the planes of the coil is 45 degree. So what happens now due to this? Due to this, initially magnetic dipole moment of the coil was in the, suppose, y axis, negative y axis. This was the initial direction of the magnetic dipole moment, and now new direction of the magnetic dipole moment is something like this. And if I plot them together, they will look like this, and the angle between them is 45 degree initially. And now coming to the magnetic field part also, what we had initially magnetic field was like this. Sorry, let's use white color. Initially our magnetic field was like this, and our initial magnetic dipole moment was like this. Suppose that was m, and this is b. Magnetic dipole was in the y direction and negative y direction, and magnetic field was in the x direction. So this angle was 90 degree. This angle was 90 degree. Now our new magnetic dipole moment is 45 degree to the old magnetic dipole moment. So this is 45 degree. So the angle between new magnetic dipole moment after rotation and magnetic field is also becomes 45 degree. So we got the angle, and now what we can do? We can find the value of the torque. So torque is M cross B, and we have M into B, and angle is sine 40, angle is 45, so sine 45 is 1 by root 2. So the final answer will be, we have the value of M, magnitude of M, we have the magnitude of field, and multiplication divided by root 3. So it will be 0.375, that value of M multiply 1 divided by root 2. And this give us 0.27. So magnetic dipole moment will be, torque acting will be 0.27 Newton meter. And if we want to find the direction of the torque, then we can easily find out that as our initial torque, our magnetic dipole moment now, which was initially in the, we can say, in the y direction, now uh, it is now in the xy plane. It is now in the xy plane. Let me draw the xy plane like this. This is our xy plane, and now our magnetic dipole moment is something like this. It is at 45 degree from the x-axis and 45 degree from the y-axis. So we can write it like this, that when only I'm only writing the direction. Initially it was in the minus j, and now it one component of it, magnetic dipole moment will be in the x direction, and one component in the negative y direction. So it will be direction, it will be initial direction. After rotation, direction is will be I by root j and minus j by root j. And we are taking cross product with the magnetic field that is in x direction. So I and I cross I will give us 0, and negative of j cross I will give us minus of k. So our dipole moment will be in the negative z direction, or our net torque will be in the negative z direction here in this side. So that's the end of this question. And with this, we end this video here also. Again, if you find this video useful, helpful, then do press the like button, subscribe to our channel, share this video as much as possible. And if you have any doubts or suggestions, you can put them in comment section. I will try to resolve them. If you find this video helpful, and then do consider donating some amount. Any amount will be highly appreciated. You can do it by scanning these QR codes. So with this, again, thanks for watching, and we will meet in next video.